Hello everybody, and welcome to example 4 on page 75. Let's take a minute to read this question together. So consider the linear transformation t going from p2 of r to p2 of r. So remember, p2 of r is a set of polynomials. And the definition of this linear transformation is t of p of x is 1 plus x times the derivative of p. And they'd like us to find a basis for r of t and n of t. Okay, so here's a problem that we could do directly. Okay, we know what the range and the null space of a linear transformation are, but a more straightforward way of doing this and a more systematic way of doing this is to use the fact that we have a nice systematic process for finding the range and the null space of a left multiplication operator, and to use that to help us to find the range and the null space that we're interested in. Okay, so here's the general strategy then that we're going to use. Okay, just kind of writing down what we just said. We're going to start by finding a basis, okay, for the vector space that we're interested in. Notice that it's the same vector space in the domain and the codomain. What would a nice basis for P2 of R be? Okay, how about the standard basis? And we'll think about what the matrix of this transformation would be relative to that basis. And what we're going to do is, instead of finding the range of t and the null space of t directly, we're going to first find bases for the range of L of A and the null space of L of A. Okay, and it turns out, if we think about what the connection between the linear transformation and its matrix is, that doing that calculation first will lead us directly in a natural way to the bases that we're interested in. Okay, so to do this, first thing we need to know is what this matrix A is. Okay, so let's calculate it. We know how to calculate the matrix of a transformation. So it involves starting by taking our basis vectors and substituting into our transformation. Okay, so t of 1, t of x, and t of x squared. Okay, so starting with t of 1, definition of our transformation is sitting up here at the top of the page. So if we substitute 1 in, we're going to get 1 plus x times the derivative of 1. Okay, but what's the derivative of 1? It's 0. So we're taking 0 times 1 plus x and just getting 0 as our output. Okay, and then similarly, t of x is 1 plus x times the derivative of x. Okay, but since the derivative of x is 1, we're just going to get 1 plus x back again. Okay, and then finally, t of x squared is 1 plus x times the derivative of x squared. And the derivative of x squared is 2x, so if you take the 2x and distribute it through, you're going to get 2x plus 2x squared. Okay. And to get our matrix, we need to take those three outputs and just write them as linear combinations of our basis vectors. So 0, we can rewrite as 0 plus 0x plus 0x squared. Okay, and let's see, 1 plus x, we could write that as 1 plus 1x plus 0x squared. Okay, and then finally 0 plus 2x plus 2x squared. Okay, and our matrix then, first column is going to be obtained by taking those three coefficients that I just circled. So 0, 0, 0. Okay, and you get the idea. We've done this a lot. Okay, so the next column would be the 1, 1, and 0, the coefficients that you see on the second line, and then finally 0, 2, 2. Okay. And so looking at our roadmap up here, the next step would be to find bases for the range and the null space of the left multiplication operator, LA. And we've talked in detail about how to do that in the previous examples. It really comes down to row reduction. Okay, so we'll take that matrix that we found. Okay, and you can either do row operations by hand or using a calculator or an app or something, and what you should come up with, okay, something that looks like this. Okay, there's our reduced matrix. Notice that we have two pivot positions, here and here. Okay, and how do we use that information to find the bases that we want? Okay, well, let's start with the null space this time. Okay, so the null space of L of A is the set of solutions to the system of equations that looks like AX equals 0. Okay, so that system of equations, okay, it's like taking our coefficient matrix and setting it equal to or augmenting it with a 0 on the right-hand side. Okay, so if we write down the system that we're interested in here, I'm going to use the reduced matrix. It's like just kind of putting in a right-hand side of 0, 0, 0 here. Okay, so the solutions to AX equals 0 are going to be the solutions to this reduced system that we have here. Okay, how many free variables do you see here? Well, looking at our reduced matrix, there's only one column that doesn't have a pivot in it, okay, which means that x1 is our only free variable in this case. So we'll start there. All right, and then we'll look at the actual equations in our reduced system to figure out what x2 and x3 are. So if we start with the second row, notice that if we read that off, that just reads x3 equals 0. We don't even need to do any algebra. We just kind of get the value of x3 directly. Okay, and then the first row, looking back up at our matrix again, if we read that off, that looks like x2 equals 0. Okay, and therefore, we're in a position where we can write down the null space of A, or the null space of L of A, sorry. Okay, that's going to look like the set of all vectors that have the form x1, x2, x3, and we can see from our calculations above that x1 is t, x2 is 0, and x3 is 0. Okay, and I'll rewrite that one time by just making the observation that we can factor that t out of there. Okay, and rewrite our null space like that. Okay, so I think we've got enough information now to where we can write down bases for the range in the null space. Okay, let's start with the range. Basis. Okay, so if we think back to what we did in the previous examples, writing down a basis for the range of L of A is about looking at pivot columns. Okay, so looking at our reduced matrix, we had pivots in the second and the third column, which means that we want to take the second and the third column of our original matrix A to get that basis. Okay, so we're going to get 1, 1, 0, and 0, 2, 2. All right, and what about a basis for the null space of A? Well, looking at the line above, we only need one vector to build everything that's in the null space. Okay, and so a basis, I'm going to give myself a little bit more space here. For the null space of L of A, just looks like this one vector, and I just underlined up here 1, 0, 0. Okay, good. Well, where are we in the problem that we're doing here? Let's scroll back up and just see kind of how far along in the process we are. What we just found were bases for these two things, but that's not what the question asked us. They wanted bases for the range of T and the null space of T. Okay, so how do we use the calculations that we already did to do that? It comes down to asking yourself, what information does a matrix for a linear transformation really tell you? The matrix is kind of a way of taking coordinates to coordinates. So here's what we can do to find bases for the range of T and the null space of T. We just need to reinterpret these vectors that we found as being coordinates relative to our basis. Okay, maybe just to re-emphasize the fact that these are coordinates, I'm going to sneak a little t's in here. Okay, all that would do is to turn these column vectors into row vectors, row vectors into column vectors. And in chapter 3, we're not going to make a big deal about what row vectors and column vectors are. There's not really a need to distinguish between those two. Okay, but putting the t's there just kind of reminds us that we're thinking of those as being coordinates. Okay, so what you can do then is to look at this 1, 1, 0, and I'm going to remind you up here of what our basis looked like, 1x and x squared. I want you to imagine that the 1, 1, and 0 are coefficients on these three basis vectors. What that would mean is that 1, 1, 0 would correspond to 1 times 1 plus 1 times x plus 0 times x squared. Okay, and then 0, 2, 2 would correspond to 0 times 1 plus 2 times x plus 2 times x squared. Okay, and then similarly, the 1, 0, 0 would look like 1 plus 0x plus 0x squared. And those three polynomials that I just wrote down in red should be the bases for the actual linear transformation. Okay, so let's tie it all together with one final statement here. So interpreting the vectors in the above bases as coordinate vectors, that's the key. Okay, I'm going to underline that. Relative to beta, okay, we obtain the bases that we're actually looking for. Okay, so BR, the basis for the range of our actual transformation, would look like these two polynomials. Okay, so 1 plus x and 2x plus 2x squared. Okay, this should be the basis. Whoops, try to write that a little bit better. Okay, this should be a basis for the range of t. Okay, and the basis for the null space we get, okay, by taking this polynomial. Okay, and let's see, that's 1 plus 0x plus 0x squared, so that's just a constant polynomial. Okay, that's the basis for n of t. All right, and that's what we wanted to calculate. Okay, so I'm going to circle that because that's the actual answer to the problem. Okay, so just to summarize the general strategy here, okay, we're going to do a lot of problems like this, but what we did, okay, going back to the top of the page, we started with a linear transformation. They wanted the range of t and the null space of t, so what we did was we first found a matrix for the transformation. We found the range and the null space of the left multiplication operator using kind of the standard process that we talked about in previous examples. And then, after we had those bases, we reinterpreted the vectors in the basis as being coordinate vectors and used those coordinates to build the actual vectors in the bases that we wanted. Okay, and that's a very useful systematic process that you can use for finding bases for ranges and null spaces in general.